We will present together with Francois under the help of Alexia, which prepared with us the presentation. The presentation will be on the challenge and opportunities of digital twins for power transmission assets at Hydro-Québec. You will see in this presentation there will be two parts. The first is quite an introduction of our concept of digital twins as an electrical utility. And the second part will be led by Francois, more on technical part on AI and causal and detection algorithms. So, quick introduction about Hydro-Québec. Hydro-Québec is an electrical utility in North America. It produces, transmits, and distributes electricity all over the province of Quebec. And you can see here on the right the map of the Quebec. So the particularities at Hydro-Québec is that we have all the production of the electricity which is in the north, and the main consumers are in the south of the province. So we need to have those long power lines that brings the electricity from the north to the south. So it represents more than 34,000 kilometers of power lines. And it also represents a large variety of assets all over the power grid. Based on the fact that all these fleets are aging, and we have more and more complex operation with, as an example, electrification of transport and climate change, we need to rely on efficient monitorings in order to mitigate all the hazards that could come from failure from assets on the grid in order to be able to alimент the different customers all over the province. So that brings us to the topics of today's, which is the digital twin at Hydro-Québec, and specifically here the asset digital twins. So we have developed our own definitions, which is an adaptive replica of an asset or a system that will use the dynamic data or analytic tools to understand and predict its states and behaviors in order to optimize the performance throughout its life cycle. So the main idea for us of digital twins for assets is mainly the evaluation of data in order to help all the decision makers and operations. And as you see here, we have a large variety of assets at Hydro-Québec and in the power grid. We do not need all the same maturity levels of digital twins for assets. So the development of digital twins should be driven by the value it could add to the company and to the organization. As an example, we will have different digital twins for power transformers than the one for circuit breakers, and we'll imply some different effort on it. So let me hit here. So the development of digital twin for Hydro-Québec, as an example, is a really large-scale project. It involves many different parts in the company. It came from the fields where we have a large variety of different assets. Then we have to have strong telecommunication networks. We have to have sensors implementation, communication infrastructure. At Hydro-Québec, because of the province, we not have commercial networks all over the province. So we have our own telecommunication networks that is implied. We need to rely on a strong data centralization using cloud architectures. And then we arrive to the core of digital twins, which are mainly the analytics. We're actually developing some physical and data-driven models using the science of PHM to support those activities. And the idea at the end is to support decisions and take the good actions, efficient and effective actions for the power grid. So this is the last slide of my first part that needs to introduce the concept of digital twin for Hydro-Québec transport system. So our vision is that all the operation that are mainly in asset management and grid control will be more and more assisted in the future by all those kind of digital twins. We will have two types of digital twins in the grids. The first type is the digital twins for assets. That will be our viewer of the grid, which is happening on each asset. They will need to detect, predict the failures, and all this information will come to the digital twin grid. Which it will have to run a various large amount of simulation on real time in order to support the decisions. So if we are able by the control to mitigate the risk just using the control of the grid, we'll not maybe need some maintenance. Otherwise, it will give some information to the asset management team that some maintenance need to be done on the assets before it fails. And at the end, all the control of the grids will be more and more assisted by all those type of digital twins. So this is the first part, which was more the concept of digital twin for Hydro-Quebec. And I will let my colleague Francois, that will get deeper into the data and show you some first experiment that we are actually doing on the asset.
Good. Thank you, Olivier, for the introduction. Good morning, everyone, or good afternoon if you are in Europe. In order to show what could be a digital twin to our business unit, we decided to study a simple application where we would need to detect the presence of an error on 3 signals. So it's an application to the temperature of oil in transformers. And we have 3 signals, so the ambient temperature, the current, and the oil temperature. So this would fall in the category of diagnostic. To the question, why did it happen? The answer would be because the current is abnormal, for example. So in the value chain presented by Olivier, this would fall down in the early warning detection category. So we started by looking at autoencoders, where we have our 3 input signals that are being reconstructed by the autoencoder. If the autoencoder cannot reconstruct the signal, it means that there is an anomaly in the input. Another way to use encoders would be to look at where the input points are falling in what we call the latent space. For healthy data points, a healthy data point would fall in a specific spot in the latent space. If there are anomalies, those points would fall somewhere else. So we started to study different architecture, and here we present results obtained with BLSTM, which is some kind of recurrent neural network. So first, we train the model on some part of our data in order to follow the variation of current more accurately. We had to add the variation of the current as an additional input. Here on this graph, you can see that without the variation of current, it tends to smooth out the reconstruction. However, with the variation of current as additional input, it follows better the current, which varies abruptly, and it has large variation. Second step was to set a threshold for the error detection. Here, there's still some work to be done on the data set, so we had to generate some synthetic anomalies in order to choose the threshold. And the last step of the strategy would be to test the algorithm for error detection. So here are some examples of error detection where the anomaly that we generated is just simply put one signal to 0 for an hour. So here, for example, we put the current to 0 for an hour. And in the present case, the algorithm detects an anomaly on the 3 input signals. So already with this simple algorithm, we can see that it's difficult to pinpoint the actual input signal that contains an anomaly. Same thing with anomaly on the oil temperature, where the anomaly is detected on the ambient temperature and the oil temperature. We tested another type of anomaly, which is putting the signal at a constant value for an hour. So sometimes here we get good detection rate. However, in other situations, the real signal is close to the anomaly, so it's difficult to actually detect this type of anomaly. So we get a lower score on this over simple test. We were also interested in what we call causal modeling. which is like which variable causes ANOVA to vary. This could be useful in a case of predictive model to select input variables, for example, or to regularize or explain a black box even. So we know that there have been some work being published in this direction. We think causal modeling could form the basis of prospective models. For example, to identify what is the next best action, or even quantify the effect of an action. So in our study, there are only 3 variables: current, oil temperature, and ambient temperature. But eventually, by adding other variable, we can build some form of causal model of the system. One first working definition of causality can be attributed to Granger. So it's the Granger causality, as it's called, where causality is seen as related to prediction. So if a variable x1 causes another variable x2, then past value of x1 should help better predict x2, while also using past value of x2. And we can illustrate this definition by using a simple autoregressive model with the prediction of x2 using its own past value, and by adding also past value of x1. And Granger causality can be measured by using some statistical tests on the coefficient in front of the past value of x1. So here we use an f-test in this study. On a simple simulation, we can see that the value of the f-test increases a lot when we use the lag of x1 that would cause x2. Same thing with additional lags of x1. However, if the coefficient in front of x1 is decreasing, so is the jump in the value of the f-test. So at some point, it's becoming harder to detect. Also, if we add useless additional lags to the model to test for causality, we can see that the test is also becoming less sensitive. So that could be some limitation for the usage of this type of model. We applied it on a window on our data, a window of 3 days. And here we just display the input signals. So we have some variation, and the value of the test applied between 2 variables. So for example, here in this graph, you can see that we have a high statistics for the test. And that says that the current would influence the oil temperature. Same thing here with the ambient temperature that would influence the oil temperature. And the current and the ambient temperature are not so related together. So when we move this window through time, we can see that the causal link is not necessarily always stable. For example, the relationship between ambient temperature and the oil temperature is not so clear actually through time. And same thing goes for the relationship between ambient temperature and current. Going back to the autoencoder, we ask ourselves, is there a physical reality that is structuring the latent space that was learned by the autoencoder? So here it's about AI with some form of physical modeling. So in order to investigate, we projected the training point for a specific transformer here in the latent space and looked at the first two directions in this latent space by applying PCA on these data points. And we could see that by adding color to the points, that one direction in this space corresponded to the current, and another direction in this latent space corresponded to the ambient temperature. However, here, those two axes were orthogonal, which means that they seem to be independent. And by applying another causal discovery algorithm, we could see that we could find the same result. Ambient temperature and current, seen from the point of view of the algorithm, seem to be independent. For another transformer, we use the same method, and here we can see two modes of functioning for the transformer. One for the summer here, and one for the winter. Here the color corresponds to the seasons. So that's the hot season, that's the cold season. And when we look at the variation of ambient temperature here, we could see that there are two axes. And those two axes are not orthogonal to the variation of current. And indeed, applying selectively the causal discovery algorithm, depending on the season, we could measure a causal link from ambient temperature to current that is negatively correlated in winter and positively correlated in summer. So there seems to be some kind of correspondence between the causal network and the structure of the latent space here. It's difficult to obtain stable links, and we suspect that we should include other source of data in the model. And we think that by having a better causal modeling, we could certainly improve the performance of the autoencoder. And I will let Olivier conclude.
Thanks, Francois, for this part of the talk. So to give you a conclusion, so at Hydro-Québec, the initiative of digital twins has been launched, in fact, in 2018, and has involved many stakeholders in the company, as I show you on the large-scale project. What is important for us is, I think, to find a common language and goals for all the enterprise. And I think it passes also through the importance of developing a data cultures and the importance of historizing all the relevant data sets as early as possible. The primary test involving the autoencoder and causal modeling that Francois showed us show us some real challenges between the understanding of physics and AI, and how we can integrate those two in the algorithms. And we'll just finish on some future directions. So I think the main idea is to improve our asset digital twin dynamic interactions. The idea is how those digital twin will interact with the electrical power grid control and with the asset management team. There's some specific algorithm that lead the control of the grid, and there's a specific decisions algorithm that lead the asset management. Our idea is to link digital twins with those other algorithms in order to be kind of system architectures. The other thing is to design robust, certifiable, and explainable analytics to build a usage trust in long terms. So improve our PHM algorithm and go further from what we are actually experiencing. And the last things would be to improve the physics-based model and domain expert knowledge implementations in AI algorithms in order to build some knowledge from the physics and from our experts into the structure of the AI algorithms. So thanks for the attention. If you have any question, we'll be there to answer.